Guys, this is video 3.5. In this video, we're going to talk about empirical formulas. So this term empirical formula just means, or the helpful way to remember it, the simplest formula. Okay? Let me erase that. Simplest. All right, it really means simplest whole number ratio. All right, and that's what we're going to be looking at, is to figure out the ratio between all the elements in a compound. Anybody be thinking, why in the world are we learning this? Well, this actually is how scientists will figure out compounds and structures of compounds in the real world. All right, so assume 100% of the sample. All we're going to do in step one is change percent to grams, so percent to mass. Okay, step two, we're going to find the moles from the grams of each element, so the saying for that is mass to moles. Step three, we're going to find the smallest whole number ratio by dividing by the smallest number of moles, so divide by small. Number four, if necessary, multiply to get rid of fractions, multiply to whole. So the saying, when you put the highlighted pieces together, it's percent to mass, mass to mole, divide by small, times to whole. All right, so that's the process. Now you might be thinking, what in the world does any of that mean? Let's jump into a problem. All right, it's going to be taking the pieces that we've already learned in this unit, and now we're just going to apply them in a new fashion. Okay, so the first step is we're going to change our percent to grams. So this is the most important step. Do not miss it. Don't look away. Don't blink. It's super difficult. All right, so if you can get past this step, you can get past them all. 78%. We're going to change it to grams. Bam, that's it. It was a joke, a little sarcasm. Super easy, all right? So just take that percentage sign, and we're going to convert that and just change it to grams. So there could be problems where they don't even give you a percentage. They just give you grams. If they give you grams, great. You can skip step one, and you just go to find moles. So how do we find moles? If we have grams, how do we go from grams to moles? This is going back a couple of videos. Well, we need to divide by the molar mass. So I have grams of boron. So that's going to go on the bottom. And I want to get to moles of boron on the top. So 1 mole of boron is 10.81 grams. Now, where did I get that, right? 10.81? It's from the periodic table. It's the atomic mass of boron. So do the math. Now, when you do this, do not worry about sig figs and rounding until the very, very end of a problem. So for now, we're going to carry out like 3 or 4 decimals. So 7.2155 moles is what we would get when we do that division. All right, we're going to do the same process with hydrogen. The only thing that's going to change is the molar mass because we have a different element. Okay, so grams will cancel out. Forgot to do that up top. So 22 divided by 1.008 would end up giving us 21.8254 moles. Have we done anything really brand new at this point? No, we've done this. This is practice. Continued practice is what we've already done, going from grams to moles. So now we're going to divide all mole numbers by the smallest number of moles. This is the most crucial step of the entire problem. No sarcasm here whatsoever. Okay, this is the step that students will forget, and then their final answers will be completely off because they're not looking at moles. Now remember, we can't compare grams of one substance to grams of another because each element's atom size is different, right? Different number of protons, different number of neutrons, therefore their masses are different. But we can compare moles, all right? That's our counting unit we use in chemistry, so we're going to use that. So I'm just going to rewrite my information down here. So I have 7.2155 moles of boron, excuse me, and then I have, for hydrogen, I've got 21.8254 moles. Which number is smaller? The boron one, right? So what we're going to do is we're going to divide both of those by 7.2155. So the math for boron is pretty easy because we're going to have 1, right? Because if you divide by the same number, it's just 1. Hydrogen, same thing, 7.2155. Now, when we do that math, we end up with about 3.02, which we're going to call 3. All right. Now, step 4, it says, remember, if necessary. It's not necessary here because we have whole numbers. So our final step, guys, is we're going to write the formula. So I'm going to take boron. I'm going to write a 1. Now, do I have to put a 1 there? No. Okay, so for the purpose of this first example, I'm putting the 1 there just to kind of show you where I got that. And then hydrogen, we would have 3. All right, so I would have BH3 would be my final answer. That'd be my empirical formula. So ask yourself, is this the simplest whole number ratio? Can I divide these numbers down anymore and still have whole numbers? No, I can't. This is the simplest, therefore it's my empirical formula. Okay, it's a process, guys. This saying is going to be helpful. Percent to mass, mass to moles, divide by small times to whole, if you need to. Okay, so let's go ahead and try another example. So it says analysis shows a compound. This is what scientists would actually do if they ran an unknown. They could get a readout of percentages. They have a percent of part potassium, 26.5%, 35.4% chromium, and 38.03% oxygen. We need to find the empirical formula. All right. So here we go. Step 1. I'm not even going to show percentages anymore. I'm just going to write it down as grams because that's what I did in the last one. Okay, so we're assuming 100. So this is 26. I don't know why my tablet's messing up. Bear with me. I apologize. 26.56 grams of potassium. Chromium, we've got 35.41 grams. And oxygen, we have 38.03 grams. So convert to moles, right? We can't compare grams. It's comparing apples and oranges. We want to just compare apples to apples or oranges to oranges or kiwi to kiwi, whatever. So divide by the molar mass. So potassium, we have 39.01. Oh my goodness. Grams. Bear with me here. I don't know what's going on, guys. There it is. It's not what I wanted to happen. There we go. Okay. Chromium, its atomic mass is 51.99. Oops. 996 actually. And then oxygen is 16. All right, so how many moles of potassium do we get when we do the math? We should get 0.6809 moles. For chromium, we should end up with 0.6810 moles. And oxygen, we would end up with 2.3769 moles. Now remember, this next step is the most crucial step. You've got to divide by the smallest number of moles. So for potassium, I'm just going to copy my information down now. Once we get into more practice, guys, we're not going to have to rewrite our stuff in two different spots. We can just continue it along. All right. But for the sake of notes, I'm going to rewrite it. So 0.6810 moles, and oxygen is 2.3769 moles. So which one's the smallest? That would be potassium. So I'm going to divide by 0.6809. That cancels out to be 1. This is going to be 0.6809. That's going to cancel out to be 1 as well. 0.6809. This one is not going to be 1. This one's going to be 3.5. So if you have one of these numbers here as your decimal after you have divided by the smallest number of moles, then we're going to multiply to get to a whole number. So our fraction is 0.5. We're going to multiply by 2. Now let me ask you, is it going to just be oxygen that you're going to multiply by 2? Which when we do that, we would get 7. Is 1 to 1 to 3.5 the same ratio as 1 to 1 to 7? No, it's not. So you have to make sure that you multiply all of the elements by the number, okay, to keep that same ratio. So our example, we multiplied by 2. So our final formula would be K2Cr2O7. All right, potassium dichromate. So you guys go ahead and try the two U-try problems. For the sake of the video, I'm going to make a second part where I work these two out, so you can come back and check that after you have tried them on your own. If you have questions, ask.